Okay, so for this talk, I'd just like to give some big picture perspectives on where we're going in federated learning. So it's partially motivated by the contrast that I've seen in my roles working on FL in both industry and academic hats. And maybe I'll say something controversial or rash, but at least we can have some discussion, hopefully. Okay, so first of all, there are some things which are often flagged as FL challenges, but I've come to suspect might not be that serious challenges, especially in an industrial context. So let's talk about those first. So one thing you see in a lot of papers is some kind of figure like this that says, oh, here's my FL algorithm, and it performed almost as well as a centralized algorithm, and yeah, we are making progress. And that's kind of academically interesting. But if this is crucial for your business model, you are probably doing FL wrong. The whole point of FL is to make an unfair comparison because of accessing more data than the other guy, not be able to do FL equally well to centralized data on the same data. So yeah, you're probably doing it wrong if you're worrying about this. What else? A whole bunch of papers, including some of the talks in this summit, are worried about the impact of non-IID statistical heterogeneity on your model convergence and accuracy. Lots of people are worried about things like heterogeneous hardware. Lots of people are worried about comms cost. And maybe if I go out on a limb a little bit, I might say none of these things are really that big problems in some kind of industrial contexts. Why? Because nowadays we almost never need to learn a model from scratch. There is usually either some kind of foundation model you can start with, or you can pre-train some kind of model on whatever public data and use that to bootstrap your training. And then, depending on how good is your initial model, you can probably get away with only learning a subset of the parameters in the model when you actually go out to do your FL. And so what is the impact of this? Well, on the subject of non-IID statistical heterogeneity, there's a whole bunch of results now that show that this is a big problem when learning from scratch, but if you are fine-tuning a reasonably decent initial condition, it goes from a big problem to minor nuisance. So in this practical regime of not starting from scratch, we don't need to panic that much about non-IID, perhaps. And then coming to the comms cost, if we have a decent model to start with and we are only like refining a few parameters of it in our federated learning, then again, you can have orders of magnitude reduction in the comms cost because you are only transmitting a tiny fraction of the parameters in the whole model. This is a plot from one of the papers we did on this comms cost on x-axis, accuracy on y-axis. You can reduce a lot in this kind of parameter-efficient fine-tuning regime that we have already heard a little bit about in this conference. And finally, on the impact of heterogeneous hardware, everyone talks about this a lot, acts like it's a big problem, but I have seen so many good methods out there for different kinds of conditional computation that execute a kind of subset of the computation in a given neural network, and you can scale that computation up or down to address either hard instances, easy instances, or high capability clients or low capability clients. So maybe some of these things are not such crucial problems. Similarly, as we heard yesterday in the great talk from Borja, even not starting from scratch makes privacy guarantees a lot more practical. Because now if you don't start from scratch, you can do differential privacy learning, and it really works much better than how it interferes with your learning if you are starting from scratch. So again, many of the things people worry about a lot become kind of nuisances more than fatal problems, perhaps, if we are not starting from scratch. Okay, so that's some things which might not be severe problems. What are the things which are outstanding problems then? So challenges that are real bottlenecks. So one of the challenges is that at least for kind of cross-device learning in discriminative setting, which is what the vast majority of academic papers are about. They typically start off by doing something like training a CNN ConvNet to recognize CIFAR. That's kind of fine, but in reality for cross-device, you almost certainly don't have labels. So in any of your object recognition, object segmentation, detection, whatever it might be, you almost certainly don't have a label. So why are we spending 90% of our academic papers studying how to do FL in a supervised learning way, given that this is not going to happen in real life? So in the cross-device setting, basically you are not going to have labels, and so we should be focusing on how to do federated, self-supervised, semi-supervised, unsupervised something. One of these are one of the things we ought to be doing, and I commend the minority of researchers who are working on this topic. I know some of you are here, but I think more of us need to get on this topic in order to really make FL a success. What else? Another thing that's a real challenge, I think, is most interesting things are non-stationary. So in the typical kind of academic paper benchmark, you have a data set, you pretend it's an FL data set, and you do your learning and you give some number. But in reality, the data distribution is always evolving. You know, during COVID, we had new kind of language and visual concepts emerging of face masks and whatever it might have been that we didn't have before that. And we need to keep up with this if we are really deploying things in practice. Even the meaning of emojis seems to change over time. You're not allowed to use these emojis anymore, and so on. So we have a lot of conditional concept drift going on. And again, there's a minority of people who are working on this stuff. I commend you. But basically, not as many people working on this as the severity of the problem if we really want to do FL in production on real problems and not toy benchmarks. What else? Another big problem, I think, is regulatory. So this can be maybe the biggest problem for deploying FL industrially in some kind of production system. So, I mean, I won't say much about this because I think there's going to be a great talk later that will delve into the details of this. But, you know, there's all kinds of problems that arise if you can't really control and inspect the data on each worker in your federated network. So hopefully we'll find out more how to deal with that later. And finally, there's the problem of bias and fairness. So having kind of fair and unbiased AI models is a very kind of topical challenge these days. This is actually a completely unsolved problem, even in central learning. People like to say that it's starting to be solved, but we had a slightly controversial negative result paper last year, iClear, that showed that it's definitely not solved. If you go to a federated learning setting where you have even less kind of data curation control than you do in a centralized learning setting, making sure that the models come out fair and unbiased is even harder. So those are some things that I think are kind of maybe the bigger challenges going forward than some of the popular ones, but less severe ones that I mentioned at the beginning. And finally, let me close by talking for a moment about federated learning opportunities. So where are the places where we can potentially make a transformative impact? So of course, throughout this summit, we've been hearing about diverse applications from healthcare to language processing and so on. And if we can really bring federated learning to bear on those applications, that will of course be a fantastic set of impacts. But just to step back a bit and think more broadly about whether there is scope for federated learning to impact the foundations of AI. So coming back to the kind of opening point, federated learning should be about enabling radically unfair comparisons with regard to data and compute. And I think many people here probably agree with that. That might be the one less controversial thing I said. But we all just talk about it, but do we ever actually really do it? So what might we achieve if we actually really did it? So, of course, one of the things is the kind of popular foundation models these days, GPT, Stable Diffusion, take your pick. These are some of the topical things in AI, and they are mainly based on unprecedented amounts of data and compute being thrown into existing algorithms. So what about a future where we can arrive to the next generation of these kind of systems by leveraging federated learning to leapfrog them in terms of the amount of data and compute that we can throw at building the next generation language model or whatever it might be? Also today, we are mainly using neural architectures like convnets and transformers that were designed by various smart engineers. And there's a whole sub-discipline of neural architecture search that aims to compete with them through automated discovery of new architectures, which is great, and they have some cool outcomes. But I have not really seen anybody abandoning the hand-engineered ones for the automated neural architecture developments in a widespread way in practice, which I guess is because they are not that much better than the hand-engineered ones, only marginally better. But what about a future where we can really leverage the unfair advantage in data data and compute provided by FL to really do federated neural architecture search and kind of decisively come up with a better architecture beyond the next transformer or whatever it might be. And finally, one of my pet topics is optimizer meta-learning. So again, in our daily lives, we probably use optimizers like Adam and SGDM and whatnot, despite that there is a whole very active subdiscipline of optimizer meta-learning. And similarly to this neural architecture search story, these guys have derived better optimizers that can beat Adam and so on in some cases, but not enough better that people are widely abandoning Adam for kind of machine-designed optimizers. But again, what if we can leverage the unprecedented data and compute of FL to really rock the foundations of AI by having a dramatically better optimizer? That would be another really cool outcome that maybe we can discuss in some future iteration of this summit. And yeah, I'll leave it at that. Thank you.
Okay, so we have a couple of minutes for questions. One question here.
So actually, I have a question regarding fairness, that how we can solve the problem of fairness, because it is a very serious problem. Because the thing is that humans are biased.
Yes.
And because humans are biased, data is biased. And because data is biased, my model will be biased. And if my model will be biased, maybe it will amplify the bias in the maybe next model or maybe new models. So how we can solve the problem of the fairness practically?
Yeah. So yeah, that's a super good and very difficult question. I was saying this is actually still pretty much unsolved even in centralized learning, so before we get to the added challenge of federated learning. But I think one interesting insight about that recently in the centralized learning area is that if you the key thing is to optimize for the fairness on a validation set and not on a training set. Because anyway, if you do deep learning, you can fit your training data perfectly. It will have same accuracy for men, women, or whatever other aspect of fairness that you are trying to address. And the unfairness arises during validation, not during training. So you should do your hyperparameter optimization with regard to validation data, the fairness of predictions on validation data.
Thank you, Prof. Actually, I have a simple question. Can you give us a recipe whether a project should be implemented in the federated learning environment or a centralized environment?
I mean, I think that's what we've been talking about for the whole summit, right? So when your data is distributed around the world and policy or technical reasons prevent you from aggregating it, or when you just don't even have enough capacity to process it centrally, these might be the times when we want to consider FL, right?
Thank you so much for a great talk. I just have a question regarding starting from scratch.
Yes.
It's true that we don't start from scratch for image, text, video, but what about modalities that we don't have data, like PPG, EEG, biosignals, where we can find good model for those if we don't do federation?
Sure. So, I mean, I agree for some cases it's easier than others, but even for something like EEG, there is some open source EEG data, even if not a lot like in images. And so even if you start from a not very good model, it's still a lot easier than the statistical challenges you get with FL starting completely from scratch. And then for things like EEG, which you can think about as time series, there are time series foundation models and so on that you can start with before doing federated fine-tuning potentially on an EEG task.
Hello. Given the very applied nature of your research, have you looked at the intersection of like co-designing algorithms and with systems that operate well together? So let's say you have highly distributed data, you'd obviously have distributed servers, communication in different parts of the world, different speeds, etc. So have you considered looking at this sort of intersection of systems and optimization in this sense?
Yeah, that's one of the main topics of Samsung AI in Cambridge. Yes.
Have you found anything interesting as direction?
Oh gosh, found anything interesting? Yeah, so we do some things like kind of looking at hardware designs that will better support particular kind of neural architectures. Yeah, so I can't say too much about it, but it's one of the very active topics in Samsung, yeah.
Thank you.